Hello, I'm Daniel, and like he mentioned, I'm going to be talking about initializing Go packages. So just to make sure that we're all on the same page, let's look at a very simple main package. I omitted the package line just because otherwise I'm going to run out of space. This one just prints hello. What if I have a global with that same string value? Nothing exciting, same result. What if the global calls an anonymous literal function that returns that string? Same result. But this is where it starts getting interesting. What if that function has a side effect, like, for example, printing init? So that happens first, then the return happens, and then main prints that value, right? What actually happens when the Go compiler handles that case is that it sort of rewrites that code into, you still need a global value because that is the state, right? There's an init function that does the side effect and then assigns that global that you then use in the main function. Here's a more contrived example. So I'm going to let you look at it for 10 seconds and think about what might happen when you run this. So you've got three globals, right? v1 adds v2 with 100, v2 calls f increments counter and returns it, and the counter is 3. What actually happens is that the Go compiler, when it generates the init function for that package, because at the end of the day, part of the compilation step is generating code, it has some form of dependency analysis. And I am willing to bet that many of you were not aware of that. I probably don't even think about it most of the time, because Go just does the right thing for you, right? You don't even think about it. So the first thing it does is it finds the first global variable from the top that has no dependencies. In this case, counter is 3. The next one, whose dependencies are all satisfied, is v2, because v2 calls f, and f uses counter, right? It uses the value of counter. And then v1, which depends on v2, can be worked out. So it's actually the opposite direction of top to bottom. So the result is v1 is 104, and v2 is 4, which might be surprising, but it's also the only logical thing to do, because otherwise the only solution would be you have to order your globals very carefully so that the order works for what you want to compute. Whereas in this case, the dependency analysis does it for you. Here's another example. What do you think happens here? So in this case, we've got two globals, but they're functions, and they depend on each other. Show of hands, who thinks this compiles and does something? Show of hands, who thinks this doesn't compile? That's better than I thought. It does fail. The dependency analysis effectively says there's a cycle and I cannot deal with it, so sorry, you have to rewrite this code. Which, to be fair, is the only sensible thing to do here. This is an example just for the sake of showing how this works. Don't do this. You can't, even if you try. The last thing that's interesting about init package initialization is that imports, right? So if you've got a main package that declares a flag, you do have the variable that holds the value of that flag, in this case a pointer to an integer, but the state that collects what flags you've registered is not in your own package, it's in the flag package, right? So if I do flag.print defaults in main after the global init has registered that flag, I do see the flag, but I'm not holding that global value. The one that's holding it is the package flag that I imported, right? It's got a global command line, which is the one that's used by default by the top level functions like int. And then when I call its int function, the init already has initialized command line, so it just works. So the init basics are for Go, which are defined in the spec, but very quickly summarized. The imported packages are always initialized before you, because otherwise things wouldn't work. The global variables are initialized in declaration order as long as they follow this dependency analysis that I showed you. And this is all sequential. Even if you import two packages that don't depend on each other in any way, they're still initialized sequentially. There's no concurrency here. So let's look at a bunch of packages that import each other. You've got main that imports foo, bar, and baz, because I'm very original. And then bar and baz import util. We cannot initialize main, bar, or baz right away, right? We need to initialize one of the other two. Between the other two, which one should be initialized first? Show of hands who thinks it's foo. Show of hands who thinks it's util. Interesting, about a 50-50 split. Until recently, you would have both been wrong. Until recently, the Go compiler would have been, don't know, this is not specified in the spec. The spec only shows the rules that I told you, and none of the rules say if two packages don't import each other, don't depend on each other, who goes first? Go 121 changed this. The first step is it sorts, in your whole binary, it sorts all the packages by import path, so lexicographically, and then it enters a loop. It finds the first package that's not yet initialized, whose imports are all initialized, initializes that one package, and goes back to step 2. So it's an iterative process, right? So if we go back to our example, then the only two packages, like we said, that have their dependencies met are foo and util. Foo goes before util, f goes before u, right? Then the next one, there's only one other one that meets this criteria right away because main depends on bar and baz, and that's util. And then same thing for bar and baz. Baz goes first, bar goes first, then baz, and then main. So that's done. Woohoo. So in Go 121, this is fixed. Before then, it's just whatever the compiler wanted, which is fine, but I think documented determinism is probably better. And now I've been talking for about 10 to 15 minutes, and you might say, okay, why do I care? Like, what's the whole point of this? It's interesting, but how is that useful to me? Back in Go 112, Go 111, Go 112, there was an issue reported, 29.382, by the Go Please team that effectively said, command Go is too slow. Because tools like Go Please execute command Go, and this is the same command Go that you run when you do Go build. And one of the commands that it ran, for example, is goenv gomod to tell if you were inside a Go module or not. Because if you're inside a module, that would point you to the gomod file. And the reason Go Please called command Go for this is because they didn't want to re-implement the same logic, right? You don't want to re-implement the same stuff. And that way, you can also install Go Please on whatever Go version you've got currently installed, and the logic depends on what Go version you've got installed. It's not hard-coded. And there's other tools that do similar things, like, for example, if you run static check /.. it doesn't re-implement looking up those packages and finding them. It uses go list -JSON, which effectively finds those packages for you and dumps a whole bunch of JSON giving you the information about them. And every exec of command Go started with about 10 milliseconds of burning CPU in init, which isn't great, especially for Go Please, right? If you start Go Please or if you ask it for a completion, the last thing you want to do is another 10 milliseconds of waiting. Anything that blocks in the UI is bad. So this was improved in Go 113, and I'm going to show it with two commands. One is called bench command, and the other one is bench stat. And again, these commands sort of do what it says on the tin, sort of. So let's look at them. If you've got a Go benchmark, you can always run it with Go test, right? So here's a benchmark that just does something to check if a string is a number with regular expressions. And you get some output. The output is number of iterations and how much each iteration costs in terms of wall time, in terms of real time. You can do something similar with bench command. The difference is that bench command is not for Go code. It's not for Go benchmarks. It's for commands, right? So in this case, our command is goenv gomod, the same thing that Go Please would run. And then I just call the benchmark goenv because I want to. And 3 iterations because why not? And you can see the cost there. And this is with the latest Go. And the only thing to keep in mind here is that notice that when I was looking at the Go benchmarks, the number of iterations was very high because it aims by default that it aims for 1 second for each repetition of the benchmark run because otherwise if your numbers are too low, they jump around too much, right? More iterations means more stable numbers. But bench command, it doesn't do that. It just does each command once. Usually because executing commands is slow, so you don't want to do 30,000 of them. And so this is kind of similar to running go test bench with the flag bench time equals 1x. And you can see there the numbers that they jump quite a lot, which is not great. So we can actually see how this improved between Go 112 and Go 113. And I'm going to use another feature from Go 121, even though that's not the point of the talk, but it's cool. It's called Go toolchain, and you can read about that there. And what it lets us do is if you set Go toolchain to a specific Go version, when you run Go, command Go, it will first download that version and run it, and it will cache it via the module cache. So having installed bench command and bench stat, just for the sake of reference, if anybody looks at these slides and wants to try. With Go toolchain at 1.12 and 1.13, with the bench command 20 iterations and saving the results as old and new. And then we can use bench stat, which effectively collects those numbers and does a little statistical analysis to tell you what the improvement is. And you can see before we used to be at about just under 7 milliseconds plus minus 4%, a little variance. And now we're like significantly under, right? It improved by about 27%, which is pretty good. The problem with using command go further as an example in this talk is that it's a very complex program. It initializes over 115 packages, I seem to recall. So let's not use that as an example in this talk. I'm going to do a demo, and the demo is going to be about a tiny program. So let's see. This tiny program is the same one. It's not the same one. What am I saying? It is a program that has a global with a map. This map goes from string to regular expression, and then if I build it and I try it, effectively it's meant to validate some strings, right? So I can ask it, validate a number, is 123 a number? Is 123.45 a number? What about 123.foo? That's not a number, false. That's very cool advanced program, right? So what we can do since Go 1.16 is use a Go debug flag called initTrace. So let's do Go debug equals initTrace equals 1. I'm gonna make that slightly bigger if I can. Nah, I can't. And I'm going to use the H flag because effectively all I want to do is just look at what happens at init. I don't actually want the program to do anything interesting. So in this case, just show me the help. I don't care, but I just want you to do the binary package initialization when I execute you, right? And you can see the results there. That's pretty cool. This was added in 1.16, like I said. Before this, there wasn't really a way to extract this kind of information. And it shows you one line per package, which is pretty cool. So for example, you can see that one of the first things that gets initialized is, of course, the runtime. And at the bottom is our main package. So what's interesting about this is that we can see what we learned in previous slides in practice, right? So main is initialized after flag because main imports flag. And you can also see at what timestamp from the start of the program each one of those packages got initialized. And you can also see what the cost for initializing each package was, which is, I think, the most interesting bit. So in this case, the main package took about 62 microseconds to initialize. It allocated about 40 kilobytes, and that was about 264 allocations in total. Not terrible, but how would we measure this kind of improvement? Because I showed you bench command, but bench command is the whole thing, right? It doesn't do a per package, and it doesn't give you things like, for example, allocations like initTrace does. We can't really use bench stat on initTrace because, like I said, like I showed you here, the output here is nothing like a Go benchmark. It's a completely different format. So, but it is sort of similar. So here's two examples. One example is, again, initTrace with our main program, only showing the main line for the sake of space. And then we've got some Go benchmark like before. The wall clock time is kind of similar to the nanoseconds per operation that a Go benchmark gives you, keeping in mind that a Go benchmark does many more iterations. And if we use the bench mem flag for Go test, you also get the bytes per operation and allocations per operation. And that is effectively what initTrace is giving you as well, except that it's one iteration, so there's no /op or anything like that. So the data is all there. We just need a different format, right? And we need more iterations because, like I showed you earlier, bench time equals 1x. It makes numbers jump a lot. And to drive that point further, if you run initTrace 10 times on a package and you try to look at its wall clock time, for example, main, you can see that it can jump by about 2x, which is quite bad, especially if you want to get good measurements. You know, you might think, oh, I shaved off 50% of the time, but maybe you just got unlucky with one run. So I could do this manually, or I could, do a little bit of a study with paper napkin math, but I'm a bit lazy, so I want to automate that. So I wrote a tiny tool, and this idea was actually from somebody called Josh, and I will talk about him in a little bit, so not my idea. So this tool takes packages as arguments. It generates a Go benchmark to benchmark their init costs. And this benchmark loop does something a bit funky. It executes itself, the test binary, with go debug equals init trace equals 1 to capture that information. It parses those lines, that information, and it generates new benchmark results, right? Because the benchmark that is actually running is doing something completely different. We want to replace those numbers that it's giving with the numbers from init trace. So you can see, for example, with our main package again, if I run bench init, you can see that the numbers are roughly the same. You can see that the wall clock is about still 40, 50, 60 microseconds. And the number of iterations went up, but this is because, right, it's a Go benchmark, so it does run this exec and parsing and printing loop. In this case, it estimated that for 1 second, it wanted about 1,500 iterations. Why generate a benchmark, you might be asking? Because you could do this without generating a benchmark, and the answer is packages that are not main packages. Because if you've got a main package, you can build a binary and run it with init trace, great. But if your package is a library, you can't really build anything with it. The only thing you can build with it that's somewhat sensible is a test binary. And if we need a test binary, might as well use a benchmark and then use go test, right? That's the logic. And we reuse that test binary in the benchmark loop. And we can use bench init with benchstat now. So let's look at that. So we can do bench init n6. When you use benchstat, it wants at least a certain number of iterations. Usually it's about 6, because if you use fewer, basically the numbers can't be trusted. There's not enough data. So, package 6? Oh. Do I even know how to use my own tool? Oh, right, sorry, it's test flags. Bench init, I was getting confused with bench command. Count 6. So this prints the results to standard output, right? But that's not what I actually want. What I want is to save it to a file. We can see it as well at the same time with T, but I want to save those results. So let's wait for that to finish. And then let's look at what the code is doing and try to improve it, right? So the problem here is that we've got 3 calls to regexp.moscompile, but these are part of a global variable expression. So these happen at init. These happen even if I only run the h flag, these regular expressions still get compiled even if I don't use them. Something we can do, it's not the best solution, but is a solution. We can do a function called lazy compile. And this function returns another function that would give you a regular expression. And in this case, we would do return regexp must compile. And the reason we do a closure here is because when we want to call lazy compile from these 3 places, right? But we don't want them to actually compile the regular expression right away. So lazy compile. And then this is a map from string now to function that returns regular expression. And then the last thing that go please is going to tell me is here, I can't use Rx types with an index of a string right away, because that is not the regular expression value. I need to call it. And in this case, calling it, this call is what actually calls regex.mostcompile. And if we build it again, and we try it again, you can see that it still works. Let's get new numbers. And in this case, I'm going to call the new numbers new. Again, very original. Now we get to awkwardly wait for 6 seconds. You can see right away that the number of allocations per operation went down. Compiling regular expressions, it's a particularly nasty one because it needs to compile the state machine to actually do the job. So it's actually a surprisingly expensive operation. And if we do bench stat old new, success. We went down by nearly 100%. I mean, to be fair, this main package doesn't do anything else that's interesting, but this is one example of what you can do with this sort of tool. I want to show you a real-life large program. I already showed you command Go, so I'm going to show you another one called command Q. And this is similar to command Go, but for a different language called Q, which is a config language. Roger spoke about it. You might have heard about it. But basically, the only reason I want to demo it is because it's a large binary, and the init cost is not great. So maybe I shouldn't be talking about that, but it makes a good example. So let's do go debug equals init trace equals 1. And then again, I don't actually care about what the binary does. All I want it to do is to initialize its packages and then finish as soon as possible. And having it shown me the help output is a somewhat general, easy thing to do for that. Now, it does print me the help, which is not helpful, funnily enough. But before it did that, there's that init trace output, right? And what's interesting here is that, for example, we take about 7 milliseconds to initialize all the packages, which is not great. This is actually similar to how command Go was before things improved in 1.13. And we can sort of skim this and see, you know, this was 3 milliseconds, this is 6 milliseconds. We can sort of like skim this and try to find what package is at fault here. And you might be able to tell that there's a package called file types that takes 2.6 milliseconds. But this is fairly raw, right? This gives you a lot of data, and if you've got many packages being initialized, good luck making sense of it all. But the data is there. Now, the next thing is, suppose that if you do find one package that you want to dig into, right? So suppose that you say, okay, we had a package called file tabs that took 2.6 milliseconds and allocated enough bytes that I can't even count what unit this is. This is like probably 1 megabyte. So I want to look into why that's happening, right? Knowing what package it is usually not enough. You want something like a profile. So can we get a CPU or memory profile from this? We can with Go benchmarks. If you run Go test bench and you give it like bench time 10 seconds so that it runs for long enough, and you give it the CPU profile or memory profile flags, it's going to sample how you're using CPU and allocations, and it's going to output a file that you can then use with the pprof tool to inspect how the time is being spent. Can we use pprof in this way? Not really, because those flags that I just showed you are for Go test. If you try to pass those flags to a command with go debug equals init trace equals 1, that tool is going to tell you, I don't know what that flag is. I'm just a regular Go binary. I don't have that flag. Another problem is that pprof is based on samples. It doesn't, for example, with memory profiles, it doesn't count every single allocation that you do, because pprof is designed for running it for a little while on your server and getting an idea of where the cost is going. So it samples data. And init times are usually in milliseconds or hopefully in microseconds. So that's not very much, and that's not really enough time to get good sampling data. One alternative on Linux is perf here, and this is something that I'm copy-pasting from what Brian used in that issue for command Go. So let's take a look. And I'm going to slightly cheat because I don't have my speaker notes here. So, because I will never be able to remember what the command to run perf record is for Go. So here you go. What's interesting here is that perf record with a Go program is not quite enough for what we want to do here. One of the things we want to do is go max prox equals 1, because even though Go can use multiple threads and perf supports that, we only care about init cost here, and init cost is sequential, so the report gets a lot easier if you just limit Go to one thread. It just gets easier. It gets easier to analyze. Another thing we want to do is because init is so quick, we want perf to do as much work as possible. We don't care if init gets twice as low. We want as much data as possible because perf also samples. So in this case, we're asking it sample as much as you can, please, which is not going to be an insane amount, but it's still going to be more than the default. And this last flag, I forget what it does, but Brian used it, and it helped. So that's about as much as I can say. So we can do that, and it ran pretty quickly. Note how it only collected 700 samples. Again, not great because it's still sampling. And I think it also complains that its maximum frequency rate is only about 100 kilohertz, which is not very much for something that will run for a few milliseconds. But it's still sort of enough. If your init is slow enough, funnily enough, then you can sample better, right? So the worse it gets, the easier it gets to analyze. So we can do perf report, and we get a little top-down, you could say like a top-down analysis of the cumulative time spent in each function. So we can see file tabs.init spends over half of the time. Oh, it's that one there. And what we could do is we could go down and we could, this is a feature of perf. It's a Linux tool. It's not specific to Go in any way. But we could expand it and we can be like, okay, but where exactly, like what calls are causing all this slowness? Oh, there's a call to unmarshal. So there's an encoding business that takes nearly 13% of all the init cost. That's not great. And then we also seem to be doing some evaluation of Q values, which is also taking about 40%. Not great. But this is kind of similar to the data that you would get from a pprof. With a pprof, you would do top, and it would tell you like the top 5 or top 10 functions that are taking time. So this is kind of similar. And you can learn more about perf report to see what kind of visualizations you can do with it. I'm a noob at it. That's about as much as I learned how to do. But it's usually enough to sort of get an idea of what code you need to improve. So in this case, what I would do is I would go to those functions, try to see why they're so slow, and then use bench init and bench stat to benchmark and try to see if my improvements actually made a difference in the numbers or not, right? Because the key of performance optimizations is measuring, because otherwise you're just guessing. Now, I did mention the name of Josh earlier, and the reason for that is that this whole idea for a tool and for, you could say, even a talk, came from him, because he was like, well, init cost and Go packages are kind of hard to measure and to investigate. And he did a blog post in 2019 called Benchmark Init. And in it, he said, what about, and just for the sake of context, this is before inittrace existed. So inittrace came later. There's a reason why we try to do this, which is a bad idea. It's before then. So he said, what if we write a Go benchmark that does this in a loop? It forces the runtime to mark one package as not initialized, because when your benchmark starts, like you're already running the benchmark, all the packages are initialized by design, right? Because it's a Go binary. So we need to force the runtime to make it think that the package you want to benchmark is not initialized. And then you want to force the runtime to re-initialize it, because the runtime only tries to do this when the program starts, right? When the binary starts. And the reason this works is because as of Go 1.12, I think this has changed since then, especially with the Go 1.21 changes. As of Go 1.12, Jesus, half a decade ago, COVID hits a different way. You basically, the compiler generated a little bit of code for each package to effectively keep track of whether this package is initialized and actually initialize it. So the two lines that are most interesting there is calling init.initializers. It's a very funky name, but that's compiler engineers for you. That's what initializes the globals. It's effectively generated code that does that dependency analysis, blah, blah, blah. And then the next thing it does is it calls all of your init functions in order, right? The other thing that's interesting here is that it keeps track of whether or not your package has been initialized, because in the middle of that function there is, for all of my imported packages, initialize them. But you can always have like 3 packages that will import flag, and you don't want to initialize flag 3 times. You only want to initialize it the first time. So he said, let's do something horrible, like truly, truly horrible, and force the runtime to do this for us. And the way to hook into the runtime to do that, and please don't try this, like don't take this away from the talk, it's just a demonstration. You can use go:_link name to effectively tell the Go linker, oh, actually, this declaration that I've got here, I want you to make it point to this other thing somewhere else, which could be another package. And in this case, what I want to do is benchmark the HTTP package. The HTTP package's init function, or init cost. So I want to grab its init done integer counter, the one that goes 0, 1, 2, as you actually initialize the package. And I want to grab its init function. And its init function, for the sake of clarity, it's this one function that does everything else. It's not your init function. It's sort of like the mega init function that does everything for the package. And then the benchmark is, quote unquote, simply setting that integer to 0, running the initialize function, and then start over. Now, before I go to the next slide, some of you might be guessing why this is horrible. I mean, Go link name is bad enough as it is. But you might be thinking why this doesn't actually work in practice. And the reason it didn't work is global state. And I'm going to show you that same example with flag that I showed you earlier. And this creates, when I do flag.int, this adds state to the flag package, right? In this case, it declares a flag. If I try to do that twice, even if I use a different variable in my package, that panics in flag, because in this case, flag doesn't let me redeclare the same flag twice. This is for the sake of not letting users shoot themselves in the foot, but in this case, we want to shoot ourselves in the foot. And the sort of the best, what's the word? Sort of the best, what people usually do to add safety guarantees, that's what's getting in the way, you could say. There's also another problem that's actually surprisingly common, and it's if your init functions append or grow something that's global, and then you're trying to benchmark that, the more times you run that benchmark, that forces reinitialization in the same process. You're just making the global memory bigger and bigger and bigger. And this is really bad, apparently, if you want to benchmark something, because if you say, you know, if you want to run the benchmark more times so that you get better data, you actually get worse data. Things are getting slower. So that was fun to investigate, but looking at it, looking back at it, it's almost obvious why this is happening, but that's sort of like the killer here. That's what makes this whole idea pointless. It was interesting to implement, but it had to be burned. It is worth noting, though, that because this was a regular Go benchmark running quote-unquote regular Go code, even though it was code that we shouldn't be calling directly, pprof actually worked with this. So maybe this is the only saving grace of that approach, if only it didn't have those two fatal flaws. But it is still a flawed design, and it's been buried since then. If you go to bench init and you look at the history, you can still try to use it, but good luck with that. There is one last thing that I want to talk about, and it's next steps, because I showed you how you can use bench init and bench stat to get some numbers and compare them. And I also showed you how you can use perf to sort of get some information about where the time is being spent. But it would be really nice to be able to just use pprof, because to be honest, I don't want to learn perf record or perf report. And they're Linux tools, right? I can't be like, in this room, maybe about a third of you use Linux. So the rest of you are going to be like, can't use that, right? Unless I run a Linux VM, which is kind of, if you want to benchmark something, it's not great to begin with. So one idea would be for pprof support with this init trace and bench init approach would be to have your, the binary that you're benchmarking, in this case the test binary, but it could be any binary with the right init function, have it start the profile, the pprof profile somewhere, and that is one of the question marks, after initializing runtime pprof, because pprof is itself Go code. It still needs to be initialized, right? So you need to start the profile somewhere after that, but before your packages, because otherwise you're not measuring anything. You want to stop that profile when your main function starts and save the output to some file. Again, how? You probably instrument it a little bit, add a bit of code. And because this is sampling, you can probably try to use a very high sampling frequency, but you probably still want to run it like maybe 10,000 times and then grab all the pprof output files and merge them. I think the pprof tool supports that. I think this should work as long as anybody can figure out that first where and how on the first bullet point. I haven't thought about it hard enough, but I'm not sure it's possible. But if anybody's nerd sniped hard enough to think about this, please come and speak to me. And that is it for me. I don't want to talk for too long before I put you all to sleep about package init functions. So any questions, ideas, or complaints, or do you want me to dig deeper into any of the topics? Please feel free to say. Thank you.
Are there any questions?
So thanks for the talk. Is there no way to reset the state of a package? Because I think like what this looks like to me would be we initialize pprof, initialize everything, and then reset the state of everything else, and then reinitialize it. Like, it's not just about marking it as non-initialized. There should be a way to zero out that package.
That is a very good point. And it's a thought I also had when I was trying to overcome those two limitations in the original design in bench init. The problem is how you do that. Because the way the Go compiler does that is incredibly simple. And that is that when your program starts, the memory is all set to zeros, right? And in Go, the zero value is the initial value. So it literally does nothing about it. So you would have to generate insane amounts of glue code to reset all the globals to the right zero value for all packages. Now, I think that is technically possible. But A, it's just an insane amount of work, and B, I'm not sure that would actually work with the runtime. Because when you do that, the runtime is already running. And I'm sure the runtime wouldn't like it if you reset its global state. You could always say, then don't do that for the runtime, but then you're back to, well, but then you can't actually reinitialize everything. So then you get into this wonky state where you're doing like somewhere in between. I'm not sure if it's, my personal opinion is that it's not doable / worth it. If the compiler gave me a way to reinitialize, to sort of like make the binary go back to 0, then potentially, but I don't think that's possible. And also, the benchmark needs to keep track of what it's doing, right? I was completely forgetting about that. Like if you're iterating over the benchmark, you can't just reset its state to 0, and then what is the benchmark even doing? So yeah, that's also a small problem.
A silly idea. Could we rename the pprof to a.prof so it starts as first? Like,
could we what? Sorry.
Like so it's initialized as first.
I don't think you would be able to, because the problem here is that initializing a package is effectively running Go code, right? And how do you run Go code before the runtime is ready? I mean, this maybe goes back to what I mentioned to Roberto, is maybe you don't care about the runtime, maybe the runtime is never benchmarked. That's probably fine. So that might fix the problem of like exactly how is, like when is the pprof profile started. The how would still maybe be the bigger question. Maybe you could instrument the pprof package to add like another init function that does this for you. That might work. I might try. I'll let you know.
Hi. So it seems to me that a lot of the technical problems with improving this are trivially solved by doing it upstream, like integrating with the testing package, which can then just hook into the pprof package and do anything we want, like basically trivially. Have you talked to the Go team or anyone about just getting first-class support for benchmarking init stuff, which like ideally doing like go test dash init bench, and then you just get it in a nice way?
That's not a bad point. I think the easiest answer is that's more work on my part. Even though like it sounds like I did a lot of coding to get this to work, but actually bench init is maybe like 200 lines of Go code in total. And the testing package is surprisingly complex. It generates code to then run your tests and benchmarks, right? It's a surprisingly complex bit of code. And I think the other aspect of this is I saw them working on init trace, and I was like, that's so close to what I need. So I was like, can I get it close enough where I can do what I want? And I sort of did. And I think upstream would be fine to say, init trace sort of gets you most of the way there. So having first-class support beyond init trace is not a priority compared to all the other things that are on fire. But it's probably a good point that I should raise an issue about this. We could also talk about the interface. It's not clear to me how you would, yeah. But it is a good point. Like if you want to do this properly, like for example, instrumenting pprof, that probably shouldn't be a third-party tool. That probably should be part of upstream, yes. Lunch in 3, 2.
So I guess it's lunchtime. Thank you, Daniel.